Okay, hello everyone. Welcome to this live problem solving session for the course Introduction to Galois Theory, which is instructed by Professor Krishna Hanumanthu. So, this is week 6, and as usual, before doing some sample problems, I want to recall the topics of week 6. So, let's quickly list down the topics of week 6. So, in this week, we started with the proof of characterization of Kumar extensions. So, the proof of Kumar, if and only if it's cyclic. So, that theorem itself involved two parts, and we have done it in two steps. So, we have completed this part in the first lecture, or maybe both first and second. And after this, we move on to the cyclotomic extensions. So we basically defined what do we mean by cyclotomic extension. So it is basically we need to assume the setup. So F is a field with either characteristic of F is 0 or characteristic F is P but P does not divides N. So this is the pre-assumed setup. Then with this setup we have defined the cyclotomic extension of F, or more explicitly the nth cyclotomic extension of F. So okay, let me put this as star, this setup. So this we will assume throughout. So the nth cyclotomic extension of F is basically just the splitting field of a polynomial. So is the splitting field of the polynomial x power n minus 1 over the base field F. So that is the definition of the cyclotomic extension. Then we want to prove some properties of this extension. So the first thing is the roots of the polynomial so the roots of the polynomial x power n minus 1, uh, this forms a cyclic group. And using these facts we have proved that uh, the Galois group of the nth cyclotomic extension is an abelian group. And so basically we have proved the Galois group of x power n minus 1 over the base field F. Uh, this is this can be embedded in the group Z mod nz, the multiplicative group of Z mod nz. Sometimes we denote this as U of n or U groups. And this map is isomorphism when the base field is the field of rational numbers. So Galois group of x power n minus 1 over Q is isomorphic to this. So these two things we have proved. So in particular, this says that the nth cyclotomic extension is an abelian extension. So that means it's a Galois extension, and the Galois group is abelian. So this comes from this first fact. So nth cyclotomic extension is abelian. Then we have defined cyclotomic polynomials. So we have denoted this as phi nx. So this is basically the mm, irreducible polynomial of this of a primitive nth root of unity, or we can write this as product of x minus alpha, where alpha is a primitive nth root of unity. Then we have seen several properties of these polynomials. Like this polynomial has integer coefficient, and initially, for if you see for n equals to 1, 2, 3, 6 up to 6, then you may assume that its coefficient can only be minus 1 or plus 1, but that is not true. In fact, it has been proved that any integer can be uh, if you pick any integer, then it is a coefficient of some cyclotomic polynomial. So there is a result of that kind. This is the first property. Second, that its degree is basically the Euler phi function. So this is Euler's function, and also this polynomial is irreducible over Q. So we have seen these properties, and yeah, I also forgot to mention one thing from here. Uh, so the cyclotomic extension is basically denoted by, so in case of Q, we will write Q adjoint a primitive nth root of unity, and this degree is basically cardinality of this U group, and this is basically phi of n, Euler's phi function. Okay, then these are the topics from the cyclotomic extensions. And after that, we move on to the topic of solvability, which is our final task, that insolvability of quintics. So we started with a couple of definitions, uh, like what is simple radical extension, then what is radical extension, and then after that, what do we mean by an element to be solvable, and using that definition we have defined when an extension is solvable, and also some examples. Then we have proved one result, like if k over f be field extensions, and suppose both are of characteristic 0. So if and also suppose the degree of the extension is 6, then we have proved that k over f is solvable extension. And in fact we have proved which is something more general. So we have proved that uh, k over f be a field extension, and also we are assuming characteristic 0 because we don't want much complexity here. Then k over f, if k over is a cyclic extension, then it has to be solvable. So again, cyclic extension means its Galois extension as well as its Galois group is. So that is the definition of the cyclic extension. So these are the main contents of this week. Now let's try to solve some sample problems based on these topics. Okay, so let's start with some easy problems. Then maybe we can do some hard problems after getting some interest. So from the school days, we know one result that so we know that we usually denote omega by cube roots of unity, right? So cube roots of unity, and basically there are two primitive cube roots of unity, which is omega and omega square. And basically if omega is -1 plus uh, root 3i by 2, then omega square is the other conjugate, -1 minus root 3i by 2. Then we know that this sum 1 plus omega square is basically 0. So what does this mean? So this means if we so 1 is also a cube root of unity, but it is not primitive. So this says the sum of all cube roots of unity is 0. Is 0. So what happens if we take instead of cube roots of unity, if we take nth roots of unity, then what can we say about the sum, right? So the first problem is, so let n be a positive integer which is bigger than 1. Okay, then prove that the sum of all nth roots of unity nth roots of unity in C, right? Because we are not talking this about any arbitrary field, just our working field, which is complex numbers. So unity in C is 0. So that is the problem. So we already know for cube roots of unity it is true. But here we want to say that it is true for all nth roots of unity, but n has to be at least 2. So for n equals to 2, you can directly say, because for n equals to 2, the square roots of unity, and which are -1 and +1. So obviously their sum is 0. But for higher n, it is difficult to do by hand. For some n you can do, but if you increase the n, it is definitely it is difficult. So how to do it? So what is the nth root of unity? So let alpha be a primitive nth root of unity. Okay, then using alpha we can get all other nth roots of unity, because they forms a cyclic group that we have already seen. So then alpha square dot alpha power n minus 1 comma alpha power n, which is basically 1. So these are all nth root nth roots of unity, right? That we know because these roots forms a cyclic group. So now since alpha is primitive, uh, since alpha is a primitive nth root of unity, nth root of unity, so alpha is a root of x power n minus 1, right? So but what is x power n minus 1? So x power n minus 1 equals to we can write this as x minus 1. So I am using bigger x. So x minus 1 times 1 plus x plus dot dot up to x power n minus 1, right? So this is the formula. So alpha is a root of this polynomial, but alpha is also a primitive nth root. So alpha power n equals to 1, but alpha power I is not equals to 1 for all I which is strictly less than n, right? So this is the definition of primitive nth root of unity. So alpha satisfies this equation. So alpha satisfies x power n minus 1 equals to 0, but alpha is not equals to 1 because alpha is primitive. So alpha satisfies this, means alpha satisfies this right hand side, but alpha is not equals to 1, so alpha cannot satisfy this. So this implies alpha satisfies 1 plus x plus dot dot x power n minus 1 equals to 0. So what does this mean? So this is 1 plus alpha plus dot dot up to alpha power n minus 1 equals to 0. But this is what we exactly wanted, right? Because this is a nth root, this is also another nth root. So there are total n elements and each of these are nth roots. So this completes the proof. So sum of all nth roots of unity is 0. This is not only true for cube roots of unity, this is true for all nth roots of unity, but n has to be at least 2. So we are talking about sum of nth roots of unity. So sum of nth root is 0. But instead of sum, what will happen if we take product? So that is also a valid question, right? So what will be product of all nth roots of unity? So this is the second problem. So again, let n is bigger than 1 be a positive integer. Then prove that the product of all nth roots of unity in C is basically minus 1 power n plus 1. So it will depend on n. Basically depend on the parity of n. N is even or n is odd. So sum is 0, that we have already proved, but the product is minus 1 power n plus 1. So how to do this? So we already know that the primitive nth roots of unity uh, forms a cyclic group. So this can be done using just group theory, and also this can be done without group theory. So I will do in both ways, but let's use the group theory part. So we know that the nth roots of unity forms a group. So this forms a cyclic group, but we just need that it forms a group. Unity forms a group. Okay, so let G be the set of all nth roots of unity. So if we use the notations as in the lecture, it is just the cyclic group generated by this. So this is just 1 zeta n square dot dot so on zeta n power n minus 1, right? So this is the group, and order of this group is n. So order of G is n. Now there will be two cases, n is even and n is odd. So let me write down case 1 here. So n is odd. So n is odd. So uh, by Lagrange's theorem for groups, G cannot have an element of order 2. So by Lagrange's theorem, G cannot have an element. Okay, so I should write in. So G cannot have an element of order 2. So that means thus every non-identity element, so G cannot have an element, thus G cannot have a non-identity element which is self-inverse, which is self-inverse, means whose inverse is itself, right? Because if x is equals to x inverse, so that will imply x square is equals to identity. So that means order of x has to be at least sorry, at most 2. So that means order of x is 1 or 2, but it has no element of order 2. That means only identity element can be self inverse. So it has no non-identity element which is self inverse. Thus uh, every non-identity element, okay, we need that it is a cyclic group because we need the abelianness. Okay, thus every non-identity element can be paired with its inverse. So if we take the product A belongs to A such that A belongs to G, so basically we can remove the identity element. So this is same as A such that A belongs to G minus its identity, which is 1. So let me write 1 just, right? Because in the product 1 will not give you any additional thing. So we can remove the 1. But again, this can be paired as A times A inverse, right? So we can just collect the elements with their inverses, and their product will give you 1. So the whole product will give you 1. So when n is odd, this product will be 1. And in the case 2, n is even. So this implies there exists only one element of order 2 because G is cyclic. So there are exactly 2 elements which are self-inverse. So, and this element is basically minus 1. So this is minus 1 because minus 1 is will be there, which is uh, square root of unity because n is even. So in this case the product is, so this is just you take the identity element and the order 2 element out, and you take the product such that A belongs to G and order of A is bigger than 2. So this part will be minus 1 and this part will be 1. So this is ultimately give you minus 1. So all over product of A belongs to G is minus 1 power n plus 1, where n is the order of G. Right? So this is by splitting in the case where n is odd and n is even. So this is purely a group theoretical fact. Now So we can also do this by without using group theory. So let's do that also. So we know, so let alpha be a primitive nth root of unity. Then we know that 1 alpha dot dot alpha power n minus 1 are all nth roots of unity. Now we want this product 1 alpha alpha square dot dot alpha power n minus 1, right? We want to evaluate this product, but this is same as alpha power 1 plus 2 plus dot dot plus n minus 1, or instead of 1 we can write this as alpha power n, right? Then this will be plus n, and this is same as alpha power n times n plus 1 by 2, just the usual formula. Now how to evaluate this? So this we can write as so we need to split it in two cases. So n is odd. So when n is odd, so basically it is alpha power n whole power n plus 1 by 2. So since n is odd, n plus 1 is even. So n plus 1 by 2 is an integer. So this we can write. And if n is even, then we can write it as alpha power n by 2 whole power n plus 1. Because n is even, so we can divide it by 2. Right? Now, what is this thing? So alpha is the nth root of unity. So alpha power n is 1. So this is 1 power n plus 1 by 2 when n is odd. And what about this? Alpha power n by 2. So alpha is primitive nth root. So it will imply alpha power n by 2 is primitive uh, square root. And what is the primitive square root? Which is minus 1. So this is just minus 1 power n plus 1 when n is even. So ultimately we are getting 1 and minus 1, because this is some power of 1, so this has to be 1, but this is power of minus 1, but this power is odd because n is even. So n is odd and n is even. And if you combine this, then we can write this is minus 1 power n plus 1. So I think I should write here alpha is primitive nth root. This implies alpha power n by 2 is primitive square root. This will follow from the definition just. So this is just you have to convince yourself using the definition. So in this way we easily got the answer. Okay, so the sum of nth roots is 0 and the product of nth roots is minus 1 power n plus 1. Okay. Okay, so before going to more involving questions, let's do this one. So this is question number 3. So this is true false type question. So let K be the field Q adjoint square root of 3. Okay, and okay, so before stating this problem, let me use this notation. So for n bigger than 1, this zeta n is a primitive nth root of unity. Okay, so primitive nth root of unity, but in which field it will be context from the clear in which I will mention. So then show that, okay, not show that, this is true or false. So then K adjoint primitive 3 root of unity is same as K adjoint primitive 4th root of unity. Yes. Yeah. So this is true or false. So K is this field, and with this field, if we adjoint primitive cube root of unity, then it is same as primitive 4th root of unity. It is true or false. Okay. So how to do this? So to check this, we need to find both these fields, how these fields looks like. Okay, so let's find this. So what is zeta 3? So zeta 3 is a primitive cube root of unity, right? And okay, let's not do this in that way. So what is K adjoint zeta 3? So this is cube adjoint root 3 adjoint zeta 3. But this is same as Q adjoint zeta 3 first, then adjoint root 3. Because both are same. We can, because both of these two things is this one. Now what is this? What is Q adjoint cube root of unity? So zeta 3 is basically, we can write, let's take this one, root 3I by 2. So this is Q adjoint minus 1 plus root 3I by 2 comma root 3. But minus 1 and 2 are already in Q, so it will absorb its own elements. So this is root 3I comma root 3. But root 3 we have already taken, so this is same as I comma root 3. Okay, so we have got the left hand side. Now let's find the right hand side, which is K adjoint 4th root of unity. So K adjoint zeta 4. So again we can write this as q root 3 adjoint zeta 4. So this is same as q adjoint zeta 4 and adjoint root 3. But q adjoint, this is the fourth cyclotomic field. So this is the splitting field of x power 4 minus 1, which is same as x square minus 1 and x square plus 1. So uh, we already know. So the primitive fourth of root of unity is just iota. So this is simply q adjoint iota comma root 3, and this is same. So this one is easier. So they has to be equal. So this is true. Okay, now maybe we can do some interesting problem. Means it is difficult a little bit. So this is problem number 4. So okay, let n greater than 1 be a positive integer, and let f over q be a field extension, be a field extension such that the field f contains uh, contain the nth roots of unity. Uh, okay, we need to assume n is odd. Okay, so let me write this first. Nth roots of unity, and we need to assume n be an odd positive integer. So be an odd positive integer. So f contains all the nth roots of unity, then show that f contain all 2nth roots of unity. Okay, so what is this problem? So f over q is a extension, field extension. N is odd, and the elements of x power n minus 1 means the roots of this belongs to f. So we need to prove that roots of x power 2n minus 1 also belongs to f. Right? That is the problem. So roots of x power n minus 1 is in f implies roots of x to the power 2n minus 1 is also in f. So where n is an odd positive integer. So how to do this? So here we just have to use some observation. So let the nth roots of unity in F are basically 1 alpha dot dot alpha power n minus 1. Okay, so now observe that the polynomial x power 2n minus 1, this is basically x power n whole square minus 1 square, right? So this is x power n minus 1 times x power n plus 1. So something is a root of this part, uh, that will imply the negative of that is a root of this part. So how to write this? So if r is a root of x power n minus 1, so this is if and only. If and only if minus r is a root of x power n plus 1, right? Because r power n minus 1 is 0, so this will imply minus r power n, which is equals to minus of r power n, because n is odd, so this will be minus 1. So this is just observation. So thus minus 1 minus alpha dot dot minus alpha power n minus 1 are roots of the polynomial x power n plus 1. So for this polynomial we have n roots, which are this one, and for this part we have other n roots, which are this part. So altogether we have 2n elements. So these can be candidates for the roots of this, but all these roots are they distinct? So now uh, so this n elements itself distinct, so that will imply these n elements are distinct. But what about their intersection? Can they coincide? But the fact is they cannot coincide. So let me write down this, then I will give the justification. So therefore plus minus 1 plus minus alpha dot dot plus minus alpha power n minus 1 are the all 2nth roots of unity, and they are all in F. And also they are distinct as, so if we take some alpha power I and its nth power, it is 1, but if we take the negative one and if we take the nth power, it is minus 1. So they cannot coincide. So this will imply alpha power I cannot be equals to some minus alpha power j unless they are 1. So they has to be distinct. So if contains nth roots of unity, means if contains roots of this where n is odd, will imply if contains root of this also. Yes, and altogether it will imply if contains all 2nth roots of unity. So most of this part of this problem is just observation. You just have to convince yourself. Okay, so this was problem number 4. Okay, let's do something more general than this one. So it is problem number 5. Okay, so let m and n greater than 1 be two positive integers, and suppose that their coprime means their GCD is 1. Then so that the splitting field of x power mn minus 1 over q is same as the splitting field of x power m minus 1 times x power n minus 1 over q. So we have two polynomials, x power mn minus 1, and the other one is x power m minus 1 times x power n minus 1. So both these polynomials have the same splitting field over q. So that is the problem, where m and n are two coprime integers. So how to prove that both these polynomials have the same splitting field? Okay, so let uh, k be the splitting field of x power mn minus 1 over q, and let L be the splitting field of the other polynomial. Splitting field of x power m minus 1 and x power n minus 1 over q. Right, now we want to show that this field k is equal to the field L. So how to prove this? So what is k and what is L? So now k is basically the mnth cyclotomic extension. So q adjoint zeta mn, right? And what is L? So L is splitting field of this polynomial, but this is product of these two polynomials. So it must contain all the roots. So it must contain a primitive mth root as well as a primitive nth root. So it must be zeta mn and zeta n, zeta m and zeta n. And we want to prove that these two are same. So how to prove this? We need to prove zeta mn is in this field and zeta m and zeta n is in this field. So basically we want to prove one is subset of the other. So let's start with this one. L is subset of K. So we need to prove L is contained in K. So that means we need to prove zeta m and zeta n is in K. So we need to prove zeta m and zeta n belongs to K. But this is easy. So since zeta mn power n is a primitive mth root of unity and zeta mn power m is a primitive nth root nth root of unity. So this means these two elements are primitive mth root and nth root, and these two elements are in K, and they are in K. So the other mth root and nth root must be is in K. So zeta m and zeta n must be in K because it contains one primitive mth root. So it contains all mth root. Similarly, it contains a primitive nth root, means it contains all nth roots because they forms a cyclic group. So because nth roots forms a cyclic group, so I am writing it for just one. Nth roots forms a cyclic group, right? So this proves the one direction. Now what about the other one, K subset of L? So what we need to prove? So we need to prove this containment. K is subset of L. So if we can show that zeta mn is in this one, then we are done. So we need to show zeta mn belongs to L. But how to prove this? Or in the other words, it is enough to show that it is enough to show that the field L contains a primitive mnth root of unity. Right? Because if it contains a primitive nth root, then it will contain all mnth root. In particular, it will contain zeta m. So how to prove it contains a primitive mnth root? So what I want to prove is our claim is zeta m times zeta n is a primitive mnth root of unity. So let's prove this claim. Then it will prove what we wanted to do. So for to prove it is primitive mnth root, first it has to be mnth root, right? So what is zeta m times zeta n whole power mn? So this we can write zeta m power m power n and zeta n power n whole power m, and this will give you 1. So it is a mnth root. Now why it is primitive? So to prove that, uh, to prove zeta m times zeta n is primitive mnth root, we will show the group generated by this element has order n, has order mn, right? Because a primitive mnth root, if it is a primitive mnth root, then only the cyclic group generated by this will have mn elements. So we already know. So by star, so by star, cardinality of G is less equals to mn. But we need to prove its cardinality is exactly mn. So now uh, zeta m times zeta n whole power m is zeta n power m, right? And is a primitive nth root. And why it is primitive mnth root? Because the GCD of m and n is 1. So this implies G contains an element of order n. So this implies n will divide the order of the group G. So this is by Lagrange's theorem. And similarly, G contains zeta m power n, a primitive mth root of unity, that means an element of order m, right? So this will imply m will divide the order of the group G. So this is by Lagrange's theorem. Order of the element must divide the order of the finite group. So because it comes from the Lagrange's theorem, like the order of the subgroup must divide the order of the group. So in particular, order of the element must divide the order of the group, because you can take the cyclic subgroup generated by the element. So we are getting both. So both m and n divides G. So that will imply LCM of mn must divide G. But what is LCM of mn? This is just mn, because their GCD is 1. Right? And order of G is less equals to mn. That we have already proved, but it is divisible by mn. So order of G has to be mn. So we have proved our claim. So we have proved that zeta m times zeta n is a primitive mnth root. So zeta m times zeta n is a primitive mnth root of unity. And zeta m times zeta n is obviously is in L. So K is subset of L. Thus K has to be equals to L. Both the splitting fields are same. Splitting field of this one and splitting field of this one both are same. Okay. So if you observe the proof, then you can conclude another statement. So let me put that as remark. So from the above proof, observe that uh, GCD of m comma n equals to 1 implies uh, zeta mn zeta m times zeta n is same as so you can say in some sense these are same. So this product will give you a primitive mnth root of m. Okay, not me. Let me not write in this way. It will mislead. So if alpha is primitive mth root of 1 and beta is a primitive nth root of 1, this will imply alpha times beta is a primitive mnth root of 1. So product of two primitive mth root and primitive nth root will give you primitive mnth provided GCD of m and n is 1. So that is what we have proved in the last claim. So you can write it as a separate proof, but I have included in this problem itself. I think that's fine. So in particular, this using this problem, you can prove the previous one, right? Because here we are talking about if contains nth root, if contains nth root, then f will contain 2 nth root. So if contains a nth root alpha where n is odd, then a primitive 2 nth root will be product of alpha with minus 1. So minus alpha will be a primitive 2 nth root, and that is itself in f. So f must contains all 2 nth roots of everything. But we have done just by using observations. But here we have in this problem we have done the more general case. Okay, so next is problem number 6. Okay, so we have already know about the nth cyclotomic extension. So we already know the nth cyclotomic extension of q, so which is q adjoint zeta n, right? So we know that this may not be subset of R, right? But what is the largest subfield of this which is contained in R? So what is the maximal real subfield? So can we find that one? So in the next problem we are going to that. Okay, so let n bigger than 1 be a positive integer and let K be the nth cyclotomic extension of Q. Cyclotomic extension of the field of all rational numbers. Okay. Then okay, and also let L be the field Q adjoint zeta n plus zeta n inverse. Then show that L is the largest subfield of Q of K. L is the largest subfield of K which is contained in R. Okay, so we are saying that this is the maximal real subfield of the nth cyclotomic extension. So this is the exact description of that. So how to do this? So to do this, we need some steps. So let's do that in that way. So first, let's observe a couple of facts. So let sigma from C to C be defined by the conjugation map. So recall that we have done this. Then recall sigma is a automorphism of C, and not only that. So this is one thing. Second thing is if you take the fixed field, okay, not that one. So what is order of sigma? This is 2. Third one is you take the fixed field of this group generated by sigma. This is R. Okay. So these are the things this we have done in the, I think, in the first live problem solving session. So you can go back, or this is very easy. You can do it on your own also. So now now define let's say tau to be restriction of sigma to K. Then this tau is clearly in the Galois group of K over Q, right? And so this is the first thing. Second thing is what is the fixed field of this tau? So this is same as you take the fixed field of sigma and you intersect with k. So this is same as R intersection k, right? So this is the maximal real subfield of k. So we need to find this one. So we want to show this k fixed field of this one is same as L, which is Q adjoint zeta n plus zeta n inverse. So that is our task. So now how to do this? So we will do in the usual way. So we will prove uh, each of this is subset of the another. So first let's prove this one, that L is subset of K. So what is tau of zeta n plus zeta n inverse? So by the way, zeta n is nth root. So what is this? Its inverse. So this is, by definition, this is tau of zeta n bar plus tau n inverse bar. But zeta n inverse is same as zeta n bar because their product is 1. So this is zeta n inverse, sorry, my fault. So tau of zeta n inverse, oh, again I am doing mistake, zeta n inverse plus zeta n, sorry, and this is same as zeta n inverse plus zeta n. So this implies zeta n plus zeta n inverse is fixed under tau. So this implies Q adjoint zeta n plus zeta n inverse is subset of K fixed field of tau. Okay, so yeah. So we have proved the one side. So this one is fairly easier. Now the other side. The fixed field of this one is subset of L. How to do this? So here we have K. Here we have K adjoint, sorry, fixed field of this, and here we have L. So this much we know. This is same as Q adjoint zeta n plus zeta n inverse. But what is this degree? So now this A degree of this one is same as this cardinality of this group generated by tau, because by the one of the earlier results. But this is 2 because this is the conjugation map. So order of this tau is 2. And what about this one? Also zeta n. So this one is Q adjoint zeta n. So zeta n satisfies the polynomial x square. So basically it satisfies the equation x plus 1 by x minus zeta n plus zeta n inverse, right? So this implies zeta n satisfies the polynomial x square minus zeta n plus zeta n inverse times x plus 1, but this is belongs to L. So this implies this degree, which is same as degree of q adjoint zeta n over L, must be less equals to 2, because it's at this element, degree of this element is less equals to 2. What is the picture? So this thing is less equals to 2 and this is already 2, so k has to be equals to L. So this implies the fixed field of tau has to be equals to L. So this field is the maximal real subfield of the nth cyclotomic field. So this is what we wanted to. And note that this maximal real subfield, uh, this extension is of degree 2. Okay, so I will put that as remark. So this degree of q adjoint zeta n and its maximal real subfield, this is 2. This one is maximal real subfield. So from this thing you can conclude other things, that if you take q here, so then this degree is basically the Euler phi of n. So this will imply 2 has to be divided phi of n for all n greater equals to. Otherwise this extension has to be coincide. Either it is subfield of R or 2 divides the degree of the extension. So if 2 does not divides this, then it has to coincide. So one can conclude this. So if 2 does not divides phi of n, that means 2 does not divides uh, this degree, this will imply the maximal real subfield is q. Uh, no, I am making some mistakes, because if we take q zeta 4, this is q of I and here you have q, right? So this remark is not true. Let me not make unnecessary conclusions. Yeah, so this fact you can just remember. This is true, this is 5n. Yeah, this is not false. Okay, let's do one more. This is problem number 7. Okay, so let K be the field Q adjoint a primitive fifth root of unity, and define sigma from K to itself by uh, zeta 5 maps to zeta 5 power 4. Okay, then find uh, the fixed field of this one. So we have defined an automorphism, we have to find the fixed field, right? For this, you just observe that. Uh, so what is the degree? This is basically pi of 5. This is 4, right? So there are only 4 positive integers which is coprime to 5. So cardinality of the Galois group of K over Q is 4, and it's a cyclic group. And we know Galois group of K over Q is cyclic. Also, we don't need this. Okay, let's remove this. So, if okay, so what is the automorphism? Let's focus on that. So sigma of zeta 5 is zeta 5 power 4, right? So this is basically the inverse of zeta 5, or we can write the conjugate map, and we already know the order of the conjugate map. So this will imply order of sigma is 2, and by the earlier problem, so the fixed field of this one is basically Q adjoint zeta 5 plus zeta 5 inverse. That is one description. So if you want to give more description, you need to explicitly find this zeta 5 and take the conjugate of this and take the real part. Okay, so maybe we have done enough problems. Yeah, so basically these cyclotomic extensions are important as these are abelian extensions, and there are not very easy methods for constructing abelian extensions. There are several methods, but uh, this one is easier compared to the others. So that's why these cyclotomic extensions are important. Also, there is one important theorem which is known as Kronecker-Weber theorem. So which says that finite abelian group uh, is can be seen as a Galois group, uh, of a Galois extension over Q. Basically, it is a subfield of a cyclotomic field. So maybe if I wrote this, then it will be more understandable. But you can find it in any standard textbook, and the statement is very simple. Okay, so maybe we can stop today.